Okay, hi everyone. Let's get started. So today we're doing a tutorial on indexing, But first of all, we're actually going to start with a recap of some of the stuff we learned during the first week about SSDs and write amplification. And then we'll use that for one of the questions. Okay, so just to get a sense, I asked you to read, that reading from the first week. How many people actually looked at that? Just so I have a sense. Okay, so a bunch of you, so that's good. Did it make sense to most of you? Okay, so we'll do a recap of that. Ask me any questions, and then we'll do some questions. Okay, so first of all, so the whole point of that document is to teach you some ways of modeling SSD write amplification more precisely. And as we've seen, SSD write amplification is the result of garbage collection, for the most part, garbage collection operations that happen inside the SSD. And these are gonna, mess up with our application performance because they're happening in the background for the SSD to clear space for things we're trying to write and update. Okay, so how do we model this? So suppose we have an SSD with a logical address space of size L. You can store L addresses, let's say, and it has a capacity of P. Right? These can be in the same units. So this means that the fraction of usable capacity that we have in the SSD, let's call it L divided by D. Right? So that's the fraction of the physical capacity of the SSD that we can actually use to store useful data. Okay. So, so what is this L divided by P with respect to our kind of internal SSD architecture? Well, we saw that an SSD page can really be in one of three states, right? A page could be empty, or it could be invalid, or it could be valid, right? Those are the only three states. And so does anybody have a sense of how you might express this L divided by P with respect to these? Kind of the let's say the fraction of valid, invalid, and empty pages in your SSD? Okay, well, let's just kind of show you what it is. So it's this, and that's nothing too fancy. I'm just saying that the fraction of valid pages. So the fraction of usable capacity is a proportion of valid pages divided by, the overall capacity. And this I might as well have written, 100%, right, at the bottom here. Okay. Now, for the most part, as kind of talked about during the first week, we do garbage collection as late as possible when we have, very few empty pages left, right? And so, you can kind of approximate this as valid divided by, this thing here. Okay, that's the first thing. The second thing is, so when we try to reason about SSD garbage collection, right, we can reason about the worst case, or we can kind of reason about the average case. So in the worst case, all of your erase units inside the SSD are equally full. Right? Because if they're equally full, so in this case, they're not all equally full. And you can see that if there's an uneven distribution of invalid pages across the different erase units, some of them will have more invalid data, but some of them will also have less invalid data. So as long as you have this uneven distribution, it means that there's going to be some erase unit with less invalid data than others, and that's going to give you, on average, give you some nice garbage collection victims, right? Where you have to migrate less than like the average number of invalid pages per erase unit, right? So this is the worst case because here, you really don't have any erase units like this one here, right? All of them are equally full. Does that make sense to everybody? So that's kind of our worst case, and this is kind of our not worst case. Okay. So let's just reason about the worst case for a second. Okay, so you probably saw this equation in the reading, and this equation gives you, it approximates write amplification due to garbage collection based on X, where X here is defined as the average fraction of valid pages in the erase unit that you're garbage collecting. So just to give you an intuition about how this equation works. And again, this is just for intuition. So suppose I want to write a new page. This is a new page that my application is trying to write. Well, on average, to be able to write this page, well, I have to do some reclamation before. And given the proportion, so now here in this example, every erase unit has 4 valid pages and 2 invalid pages. Right? This means that for every garbage collection operation that I make, I have to migrate 4 pages. And in exchange for migrating those 4 pages, I get 2 free pages in exchange. Right? So, you kind of have to do that on average for every page that your application is trying to write. And so on average, this gives you a kind of an expression for write amplification, for the overall write amplification. In this case, it's something like 3. Okay, so this is just to give you an intuition of what this equation is actually trying to do. Okay. Does that sort of make sense? Okay. So now in the worst case, the fraction of live pages in each erase unit is just this. Because, when on average, the number of invalid pages in each block you're garbage collecting is equal to this, that describes the worst case where you don't have any good garbage collection victim to choose. Okay? Okay, so we have this to describe our worst case. But then as you saw in the reading, this worst case never actually really happens in practice. This is kind of a pathological worst case. And why is it a pathological worst case? I mean, you can kind of read it from the slide, but can somebody just kind of articulate the intuition of why this is unlikely to ever happen in practice?
Things are written in the revision sequence for that one, since randomly that same as
Yeah, that's a good intuition. Yeah. Does anybody else want to add to that? No, but it was good. It was good. Okay, so basically, suppose for a second that my writes are randomly distributed. As I write my SSD, right, and then updates are taking place, right, erase units that have been there for longer, the data will have had more of a chance to get invalidated, right? So that over time creates an uneven distribution of invalid data across the erase units, right? So in practice, even if you issue uniformly randomly distributed updates to your SSD, you would see something like this, like something like an uneven distribution of invalid data across the erase units. And this is because, so this might be the erase unit that I just wrote. I just wrote it. So there was no time has passed. So the application hasn't even had time to update anything here. But as I go to erase units that I wrote longer and longer and longer ago, they've been around for a longer time. So at this point, the application probably did, maybe had some chance probabilistically to invalidate some of their data. Right, so as erase units age, on average, they have more invalid data. That's why you typically see something like this. And that's why typically the worst case doesn't hold. And in the reading, I just gave you some equation that I actually kind of admittedly pulled out of thin air because it happens to work in practice to approximate what route amplification would be. There are more precise ways of modeling this, and I refer to them in the reading. But like for now, for this class, we don't want to do too intense math, so we're just doing this. Okay, all right, and then I showed you this graph in the reading. This graph kind of shows you how, as you vary the proportion, like the usable capacity of the SSD, you can expect different amounts of write amplification, and how this might be the worst case, but how this equation actually reflects like the real write amplification you would expect, right? This just shows you that this one is actually a good approximation relative to the blue line. Okay, I think that's all the background that I wanted to show you. Any questions about this? Yes.
Slight question. So this, like the formulas we see here, assume that when you do garbage collection, you reclaim all of the invalid pages, right?
You reclaim all the invalid pages, correct?
But then if you have like the L over P, the logical space versus physical space, that like remaining physical space can't be reclaimed, right? Because it's purposely forego the option. Like we,
I'm not sure that
so like when you said, I responded with like, when you have an SSD, we purposely restrict how many logical addresses you can actually access, right?
Mhm.
So it's not actually, like in each rating that you don't actually have access to all of the pages.
okay. So, that's a really good point. So when I talk about over provisioning, I'm not talking about specific pages that are there for over provisioning, like, right? So like over provisioning is referring to the total number of pages in the SSD that are invalid or empty. So it could be any page, but over provisioning just has to maintain that it's like, it's a fixed, it's at least this number of pages, right? But these pages can shift between the 3 different states that we've talked about. Does that make sense? Okay. I'll come back to you maybe when we start the exercises, and then maybe we'll resolve this more. But for now, let's get to the first question. And the first question is the following. Suppose you have a B tree, and this B tree is subject to uniformly distributed updates. There are 100 entries per page of this B tree. And this B tree occupies 70% of the physical SSD capacity, right? Well, the rest of it is just over provisioned. Over provisioned, I mean, like basically, you're only storing stuff on 70% of the SSD. The rest is empty. So what write amplification would you expect? And so here, basically, this question is asking you to reason about write amplification, but from different sources, right? So it's kind of from the B tree, and how does the B tree's write amplification interplay with the SSD write amplification? Okay, so think about it for a bit, and let me know if you have any questions. So I think if I understood somebody meant, so I think you meant that over provisioning is maybe we say
Let's talk about the point where what happened. It's not for assuming that all of the analysis are their claim after the garbage collector basically. But then I was thinking like, okay, well, if we're over provisioning, well then some of those invalid some of those invalid pages can't be, we're not using up all of the physical capacity. But in our calculations, we're seem to still be assuming that we can use up all of it.
you're saying that when it's garbage collection.
Yeah, because you can reclaim all the invalid pages. That's what it seems to be.
So I can actually. Software.
But then some new pages would have to become invalid if you want.
Yeah, so provisioning is like the total number of pages. Some of you, and then pages just oscillates between three different states. So basically, okay, so validate it.
Yeah.
So that means that this user provides
I wasn't here in the beginning. So, because you were, probably won't lie now. Yeah, it's
So if you look at one, like the more invalid pages you have for race units, the better. Because that will decrease your write-up. Essentially, each time you free up, because whenever you bring up all the valid pages and have to move all valid pages. It's going on, and that's not so you want to free up as much as you can while removing as little as. So then if you essentially
Feel free to discuss with your neighbor. If you have a good idea. We're going to come back together and answer this in about 2 minutes. And also, if you have a question, let me know.
But moving on.
That makes sense. It's only we just never get that. That's how we get that one bad.
Yeah, so I thought at first I thought like, we don't get. It seems like. It's kind of like something because it's better niche. Just like kind of like a part of it. Once you get more than a certain percent. We just don't like to do like.
So like once you get past that, you right. Right off like I'm losing 30%. You are losing 30%. Is it trade off? Always out. I like when you go in and that's why you like not exactly like you do.
Okay, so let's bring it together. And does somebody, so don't just throw a number in my face. Somebody tell me your reasoning, how you derived the answer. Like, what did you use? And what assumptions did you make? Yes.
The last lecture, we learned that in the worst case, a B tree will take up twice as much space as the actual data inside it. And in practice, it was about 175, I think. So
The 175 what?
175% of the actual data size. So
Well, okay, keep going.
So that means if 70% of the space in the SSD is this B tree, that means approximately 40% of that space is going to be the actual data in the tree.
Sorry, so I think you might be using like space amplification. No, I mean, so this question is always about random amplification.
You are absolutely right.
Okay, but no worries.
Yeah.
No worries. You see the answer correctly. Okay, so somebody else. What? Let's reason about random amplification. So somebody, all of you are completely confused. Can somebody at least like start us off? Yes.
The way I would start off is by going like, okay, well, one insert, which we can think of like as one logical operation, would take, well, based on the formula I see from last one, it's like on average, it would take 1 plus 1 over b plus 1 over b squared plus 1 over b cubed.
Right. Okay.
1 over 1 minus 1 over.
Which you could just call that one, right?
I can just call that 1.
Yeah.
Oh, okay. So then, wouldn't it just be the right amplification formula, but like you plug in 0.7 for L over P?
It's not far from that. Yeah. So right. So basically, right. So you start off as you observed, right? You start with the fact like we know that every update to a B tree costs approximately 1 IO. We know that they're uniformly randomly distributed, right? And we know that every application updates to the B tree is in turn going to lead, like in the worst case, to a random writes to the SSD. Right, so we can assume that the random writes to the SSD are uniformly distributed as well. And we saw that, right? So we saw that this formula allows us to approximate that before. Okay, so we take these two components and we actually just multiply them by each other. But our answer is still not complete. Okay, so here's where we are right now, right? So we said that we have this equation that allows us to approximate the right amplification for the SSD like under uniformly random writes. And we know that a B-tree update is going to cost us about 1 write IO. Okay, so we need to put these equations together somehow, but this is still not the full picture. So what do I do next? Now I have my building blocks, but I need to put them together. Somebody say anything. Yes? Okay. So you want to take this and multiply by this and then multiply by B? Yes. So, okay, so the B-tree's update cost is 1 IO, right? But each one of these IOs, right, contains B entries. Right? And whenever we measure write amplification, we want to measure write amplification from the perspective of what the user on top is trying to do. The user on top is only trying to update 1 entry. Right? So that means that, you know, for each one of these entries, we do an IO. The IO is, you know, larger by a factor of B than what the user is actually trying to do. And we must multiply that further by this factor to account for the garbage collection that's going to take place in the SSD afterwards. Right? So this turns out to be kind of your answer. And as you can see, write amplification can be massive, right? This is kind of what I wanted to show you with this. Right, so basically, if you're not careful about write amplification, right, it can be orders of magnitude higher than the work that your application is actually trying to do. Now, just to also, you know, there was a good discussion here at the front of the class. Any SSD that you buy has some over provisioning in it, right? So the logical capacity of the SSD is always restricted and smaller than the physical capacity. And different grades of SSD, right, we'll do this differently depending on what kind of performance characteristics you're trying to achieve, or the SSD is geared to achieve. Right, so every SSD has to actually manage this trade-off between space and performance. Okay, good. Any questions? Yes.
How am I supposed to interpret the 216? Is it like in order to update 1 entry in the B tree, I have to update 216 entries in addition to that one?
Basically, that's the way to interpret it. Yeah. So, like, I'm trying to write just like the entry itself, right, and I end up writing this much more than just the entry itself.
Okay. And those entries aren't necessarily like in the same page either, right?
Correct. Correct. Due to the start collection,
Yeah.
I guess. Other questions? Okay, let's continue. Okay. So now this is just a quick question. Let's do it together. Suppose that now the workload is not randomly distributed, but it's actually skewed. Okay, which mechanism of the database would allow me to significantly reduce write amplification in this case, and why? Yes. Yes. Right. So in practice, workloads are not typically uniformly randomly distributed. So you would have some skew, you'd have hot pages, you'd be able to store these hot pages in your buffer pool, and the buffer pool will be able to kind of keep pages as you're updating them. So not every update actually leads to an IO. In this case, in this sense, that the buffer pool can significantly improve your write amplification. That's harder to quantify, so right, I'm not asking to quantify that. Okay, second question. So suppose we have a B tree on an SSD, and each node, each node in each SSD page, there's just 4 kilobytes. Right, and let's suppose that like the B tree pages are perfectly aligned with SSD pages. Okay, so here's the question. You're asked to consider what would happen if instead of setting every B tree node to 4 kilobytes, so 1 page of the SSD, we actually set each B tree node to two SSD pages. Right? So the promise of this approach is that by making every B tree node wider, we're going to increase the fan out of the tree, and that's going to make the tree shallower. All right. The question is if that's actually a good idea. So now, so that's the question. Now here are assumptions. Yeah, suppose we only have reads in this workload, just to make things easier to reason about. And yeah, so we only care about read performance, not about write performance. So yeah, so is it a good idea? And then how would your answer change if this is not an SSD, but a disk drive instead? So take 2 minutes to think about it, then start discussing with your neighbors. If you have any questions, as usual, call me. So if the question doesn't make sense to you, call me. Now you have to do your analysis.
Yeah, yeah.
Okay, let's bring it together again. So, okay, so on an SSD, is it a good idea or is it not a good idea? Okay, we've spoken before. Somebody else?
We think it's not a good idea.
Okay, why?
So we first started to like, so if you like double B, right? So what would be the effect on the height? That's what we put at the start.
Okay,
If you, instead the factor is like 1/1 plus log base B2, which is practically 1. So like the height isn't gonna change as much for like large B's to handle.
right.
But now to navigate the tree, you can't just jump node to node. You have to actually be every almost 2B this time per level, right? So that's about, let's say if you're binding search, but the sort is that's at least a log 2 factor.
Yes,
And
that's excellent. Yeah, that's exactly the right intuition. So here's maybe how to reason about exactly the same thing formally. Right, so you could say that if you doubled the node size, your search cost would be the following. Right, this is the depth of the tree, and now the depth of the tree is 2B. Right, B is the number of entries that fit into one page. Now each node is 2 pages, so now the fan out is 2B. But now for every node that you actually access along the way, you're reading 2 pages. Okay, so now the question is that better or worse than what it would be if your node size is 1? Right, so and so now we have an inequality. And we can solve the inequality to show that this inequality only holds if B is smaller than 2. But that's a contradiction because B is larger than 2, right? B is typically, in the order of 10 to 100 to 1,000, right? So the answer is that this is not a good idea. Satisfied?
I still wouldn't understand why we are multiplying 2 times log and
This thing here.
here.
So, okay, so where do I get that expression? That's the read expression, assuming that I double the node size. And so why that expression is the way it is?
So why we are multiplying?
Why you multiply with 2?
Yes.
Because for every node, you have to read 2 pages. I'm counting, so this expression is just counting the number of pages that I need to read when I'm searching. Okay, let's move on to the next one. Okay, sorry. So how would your answer change if we're on a disk? Would this still be a bad idea if we're on disk? Yes?
I think this would be okay if we're on disk, as long as we stack those 2 pages at the same spot on the disks, right? Because then we can read them simultaneously and it's not actually required.
Yes, exactly. And so really to kind of say what you need to say is you say on disk, there's actually a huge difference between sequential reads and random reads, right? And so in this case, if we're actually putting these pages, multiple pages that belong to a node, like right next to each other physically on the disk, it's basically free to read the next page because you've already done all the mechanical work of moving the disk head. Okay, so on a disk drive, it makes complete sense to set large node sizes. And in fact, on a disk drive, like the B-tree node size can be set to multiple kilobytes, maybe even a few megabytes, right? So interestingly, you can tune this data structure differently for disks and SSDs, right? And everything ultimately comes from the properties of storage. Okay, question 3. Consider a table with columns A, B, and C. And suppose we're doing like buffer insertions like we talked about. So every insertion costs us 1/B. Okay. Here's a workload. We have a workload that consists of 50% queries, where these queries select something based on column A. And 50% of the operations are just insertions of new data entries. Okay, so no updates, no other kind of query, just these two kind of operations. What's the question? The question is, okay, should we employ a B-tree index in any of the columns? And then estimates the overall IO cost with and without the index. So just to give you all a hint, we said in the last lecture that B-trees optimize query performance. But what is the downside of indexes? They have two downsides. What are they? Yeah. Exactly. So basically here you're asked to, should I use the index or shouldn't I? On one hand, it's going to improve query performance, but on the other hand, it might impact my insertion performance somehow. So is it worthwhile? Okay, so think about it, discuss with your neighbor, call me if you have questions. So buffer insertions to the table itself, but in addition to buffer insertions to the table, you also have each one. Nothing. Here for this question, does it matter or not?
let's assume the index only matters for squares. So the question is something. You see,
Oh, one row each, okay,
so
cool.
we're not scanning.
That makes sense. But because the picture is one row each.
Yeah.
Okay, let's try to tackle this so that we have time for the last question as well. Okay, so should we use, so yes or no, should we use an index on one of the columns? Yes or no? Yes, over there? Okay, and if so, which column?
A.
Column A? Okay, and one?
We're always in the base looking for A, so if we use an index, it'll be a lot faster.
Okay, so yeah, yes. Now, the downside, as we discussed at the beginning, is it's going to make the cost of insertions higher. Is it going to make, how much will insertions now cost? So before my cost for each insertion was this cost. What's my new cost of insertions?
Log Q then, or log.
Yeah, log of n base b. All right, because that's the cost for VG. Okay, so what you can do is, so, you know, just to show you how to reason about this. Okay, so here's your cost without an index. Right, so without an index, each query is going to have to, in the worst case, traverse the entire table. Right, while the cost of each insertion is going to be 1 over b. This is kind of your weighted cost because, you know, 50% of your operations are queries, 50% of them are insertions. Right, so you can derive a weighted operation cost. Something like this. But here's the cost with an index, right? So with an index, each query is going to cost something like this, right? So each query is going to be significantly cheaper. Okay, but my insertions are going to be more expensive, right? Because now every insertion, we have to insert the thing to the table, but we also have to update the index. Right, so I've made queries much cheaper, but I've made insertions more expensive. But now if I calculate the average cost is still much lower than before. So overall, it's a good deal. Right? So if I significantly increase the fraction of insertions, at some point, it's not going to be a good idea anymore. But for 50% queries and 50% insertions, it's still a good idea. Does everybody buy it? Everybody on board? Good. Okay. Let's do the last one. Yeah, okay. So the last one is the following. So similar question, but different nuance. Consider a table with 3 columns, and the workload consists of the following 2 queries. So here you have 50% of your operations just select where A is equal to something, and the other 50% of the operations, they do a selection for some range over B. Right, and let's say that this returns always 1 row because, like, maybe A is your primary key, so it's unique. Whereas here, you know, it's a range query. Let's say each one of these on average returns 10 rows. Okay, so now how should we index this table? Should we use B trees? Should we use extendable hashing? Should whatever indexes we use be clustered or unclustered? Do we want 1 index, multiple indexes? So yeah, so how would you tune the indexes for this table? So think about it, discuss with your neighbor. And if you want to be concrete, assume the following data size and the following block size, right? You could actually derive the costs. And if you want to derive the costs, you can just plug in this n and this value of b to see what the costs actually are.
Oh, yeah. But you sort of only.
You can have unconstrained.
Yeah, but,
We're reading.
Okay, we have 3 minutes left, so let's address it. Okay, so first of all, let's bring it all back together. Okay, so before you even give me your reasoning, just tell me, how would you index the table? So which indexes would you use? Yes. Okay, excellent starts, correct. But you also need to say something about which one of them is clustered versus unclustered.
B would be good.
So you want, okay, so you want to do clustering in B. And A is unclustered. That's a correct answer. Good. Do you want to say why?
Because, well, B, it actually matters and it lowers the read time for B trees if it's clustered there. And
Yeah.
it would be less more, but for A, if it's consecutive hash.
Yeah. Okay, good. Perfect answer. So let's just so to recap what we just said. So right, so here this is a range query over B, and the range query is returning different logically adjacent values like based on B. So if we put, if we sorted the index like so. Okay, so first of all, we know that we cannot use a hash table in B. We have to use a B tree because B trees handle ranges, hash tables do not. Right, so we need a B tree on this. But then we also see, right, each query has multiple answers. If we use an unclustered B tree, we may have to perform one IO for each one of the result set. Right, so this is exactly what clustering helps us. Clustering is going to make sure that that this result set is on fewer pages. right? And for A, like, we may as well use, like, we could use a hash table because these are only equality queries, right? And clustering doesn't really matter. Clustering only really helps us when there are multiple entries in the result set. But here we're just returning one entry, right? So that's, any questions? Yes.
Wait, so you asked them which one should be clustered, so is there clustered extendable hash tables?
You know, like, for basically there are orthogonal design dimensions, right? So like one design dimension is like, is it a hash table or is it a B tree? It's kind of, it's an orthogonal decision whether it's clustered or unclustered. So, you know, I don't know if, like, you know, Oracle implements a clustered hash table, but like the point is you could implement it and you should think about them as orthogonal dimensions, whether it exists or not. Okay. Any other questions? Okay, congratulations on being done with another class.
Yeah.